Lesson 6, Frequency Response. Section 6.1. Frequency Response in Low Frequency Region. Experiment 6.1. Pause the video, and follow the instructions. This experiment is designed to measure the frequency response of the voltage gain GV equals 20 times log V2 over V1, and the phase difference psi between V2 and V1 of the transistor amplifier. Please refer to Lesson 11 of Electric Circuits for details on measuring frequency response. This is one of the results of Experiment 6.1. The horizontal axis is the frequency. The vertical axis is the voltage gain GV. In the low frequency region, from 1 to 100 Hz, GV increases with frequency. In the region higher than 100 kHz, GV decreases with frequency. In the mid-frequency region, GV is flat. This amplifier can be used at full performance in this frequency region. This is the other result. The horizontal axis represents the frequency, and the vertical axis represents the phase difference of the output voltage V2 relative to the input voltage V1. That is psi V2 to V1. In the mid-frequency region, V2 lags V1 by approximately 180 degrees. This is the circuit diagram of the experimental circuit. Pause the video, and check your wiring. This snapshot shows the settings for the network analyzer of the ADALM2000. Pause the video, and follow the instructions. This snapshot shows the continuation of the network analyzer settings. Pause the video, and follow the instructions. This is the experimental circuit. Note that the resistor RB has been removed from this circuit, and the signal voltage Vs has been replaced with V1. RB was used only to increase the amplitude of Vs, for the generation of smooth sinusoidal waveform by the ADALM2000. This is the equivalent circuit. In the frequency region lower than 100 Hz, we cannot neglect the capacitor CE. Let's neglect C1 because its effect appears in the region lower than 1 Hz. We can neglect HOE due to its small effect on the gain. Thus we have this equivalent circuit for the analysis in the low frequency region. By applying Hoth-Thevenin's theorem, we obtain a more simplified equivalent circuit, which has the same signal voltage VHT and the inner resistor RHT, as those in section 5.3. The voltage VI1 across RHT and HIE is given by this equation. ZE denotes the composite impedance of RE and CE. IB and HFE-IB flow into this parallel connected circuit. ZE is expressed with this equation. VE across this parallel connected circuit is given by this equation. Thus, we have this equation for VHT. And it can be reformulated as this equation. HFE-IB also flows through the load resistor RL. So this equation expresses the output voltage V2. Now we have this ratio V2 over VHT. Exercise 6.1. This is your homework. Pause the video, and answer the problem. This equation involves two important frequencies. One is in the numerator. F1 denotes the frequency that makes 2 pi F1 CERE equals 1. The other is in the denominator. F2 is the frequency that satisfies this equation. F1 and F2 are given by these equations. It is found that F1 is smaller than F2. In the case of experiment 6.1, F1 was 3.4 Hz, and F2 was 51 Hz. If F is far smaller than F1, then the circuit in experiment 6.1 has these inequalities. Then, in the ratio V2 over VHT, these terms can be neglected, and this approximate equation is obtained. Thus, the voltage gain AV in the region lower than F1 is derived as this equation. AV is constant. The phase difference of V2 relative to V1 is negative 180 degrees. If F is in between F1 and F2, the first inequality changes from the above case. Then AV in this frequency region is given by this equation. AV is in proportion to frequency. V2 lags V1 by negative 90 degrees. If F is far larger than F2, then the second inequality also changes from the above case. Thus we have AV in this frequency region. AV is again constant. V2 lags V1 by negative 180 degrees. These line graphs were drawn, by using the derived approximate equations of voltage gain and phase difference, for the experimental circuit. The frequencies F1 and F2 are at the joints of lines. Below F1, the line was drawn using this approximate equation. Other lines were also drawn using these approximate gains. The green lines are drawn using the equation before the approximation. The approximate equations simply illustrate the frequency characteristics of the complex formula. The experimental results are superimposed. They matched the calculated results fairly well. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.